All right, let's talk a little bit about the modern model of the atom, also called the electron cloud model or the quantum mechanical model of the atom. Bohr models were interesting, and they introduced this idea of energy levels to the atom, but they had a fundamental problem. When Niels Bohr was working with line spectra and examining the specific wavelengths of light that came from atoms, his model really only worked for hydrogen. When he got to helium, lithium, beryllium, and many other elements, and investigated their line spectra, they didn't come out exactly the way he had thought they would. It indicated there was some kind of missing information, some kind of missing detail in his model. And that's what the electron cloud or quantum mechanical model aims to fix. First, there's a lot of ideas that carry over from the Bohr model. A lot of previous ideas are still at play here. The center of the atom is still called the nucleus. It's still a densely packed cluster of protons and neutrons. The nucleus still has a positive charge. The protons in the nucleus still want to repel each other. The neutrons have no charge. They're in there to hold that nucleus together. All of these are ideas that are presented to us in the Bohr model of the atom. Same kind of thing you've been taught since 7th grade. Nothing new in the nucleus. The nucleus is pretty much unchanged. All the big changes happen in the electron cloud. Now, as far as the electron cloud is concerned, there's a lot that we can say that carries over. The mass of an atom is in the nucleus. The electron cloud is mostly empty space, but it is the largest part of the atom. The electrons are in the electron cloud. Electrons have a negative charge, so the electron cloud has a negative charge. The electrons are still very, very small, 1/1800th the size of a proton. They don't contribute to the mass. Now, all of these ideas that you see here are the same ideas that we had in the Bohr model. And for that matter, a lot of what you see here is exactly the same as it was in the planetary model. So the things that you learn in 7th grade, many of those things still apply. What really changes here is what the electrons are doing. Not the charge they have, not their size, not their role in the atom. Valence electrons still determine the chemical properties of the substance. And everything about those electrons is the same except what those electrons are doing. First person to come up with some information to help us understand these electrons better was Heisenberg, and the HeisenbergUncertainty Principle. The HeisenbergUncertainty Principle says that you can't simultaneously know the location and momentum of an electron. You can't know where it is and where it's going at the same time. You can only know one of the two. So if you know where it's at, you have no idea where it's going. If you know what direction it's traveling and how fast it's traveling, you have no idea where it is. Basically, in a nutshell, this gets rid of any kind of circular paths. There's no orbits, there's no electrons moving in circular paths and energy levels. Basically, what this does is tell us that the electrons are moving randomly within their energy levels. Randomly means there's no pattern to their motion whatsoever. Think about it like moths flying around a light bulb. Electrons move much the same way moths do. Moths are attracted to light bulbs just the same way that electrons are attracted to a nucleus. Moths don't circle the light bulb, so we can't assume that electrons will either. They're going to move randomly. They're going to be all over the place. Sometimes they'll be a little closer, sometimes they'll be a little further away. Sometimes moving to the left, sometimes moving to the right. Sometimes up, sometimes down. Sometimes they leave the light bulb altogether. Electrons will do much the same thing. Sometimes they're moving to the left, sometimes to the right, sometimes up, sometimes down. Sometimes a little closer, sometimes a little further away. Sometimes they leave. They usually come back because of that attraction they have to the nucleus. Their motion is completely and totally unpredictable. Schrödinger, Pauling, and Mulliken developed the idea of orbitals, and they're all working on pretty much the same thing at pretty much the same time. What an orbital is a space around the nucleus where you're likely to find an electron. It's all based on probability. Not that the electron will be there. Heisenberg told us you can't do that. But a place where they're likely to be. Think about them as rooms for the electrons. It's like taking that energy level and dividing it up into compartments. And in each one of those compartments, you're likely to find electrons. They discovered 4 different types of orbitals. S orbitals, p orbitals, d orbitals, and f orbitals. As far as the s orbitals go, there's one of those on every single level, starting as close as you can get to the nucleus on level number 1. They're the biggest orbitals. P orbitals, a little bit smaller. There are 3 p orbitals on every level, starting on level 2. In other words, level 1 does not have any p orbitals. They start on level number 2. There's 3 per level, 3 of those little compartments that we label p. D orbitals are smaller still. There are 5 of those on each level, starting at level 3. So again, level 1, level 2 do not have d orbitals. It's not until you get to level 3. And the reason for this is just space. Level 1 is closest to the nucleus. It's the smallest energy level. It only has room for one orbital, the s orbital. Level 2 gets a little bit bigger, gives you a little bit more room. Now you have room to add p orbitals to the mix. Level 3 gets a little bit bigger still, adds room for the d orbitals. The last type of orbital we know about is the f orbital. There are 7 of those on each level, starting at level 4. Again, level 1, level 2, level 3, they're too small to have f orbitals. Once you get to level 4, you got a little extra room. You can fit the f orbital in there. So levels 4, 5, and 6 and 7 have these f orbitals. Sometimes it's interesting to think about it as an upside down pyramid. In level number 1, it's your smallest level. There's only room for an s orbital there. When you get up to level 2, it's a bigger space. So you have room for that s orbital, and you've got room for the p orbital as well. Get up to level 3, bigger still. We have room for the s and p, and we can add that new d orbital to it. Level 4, bigger still. Now we have room for all 4 types. Level 5, 6, and 7 would contain s, p, d, and f, and new orbitals. So the level 5 would introduce a new orbital. We're not entirely sure what that is yet. That same orbital will carry over to level 6, and there would be a new one. Again, we don't know what that is yet, and so on. So again, in the quantum mechanical model, the modern model, these energy levels are divided up into orbitals. Orbitals are places where you are likely to find electrons. Okay, not that they will be there. Heisenberg said that doesn't happen, but that they're likely to be there. Along comes the Pauli exclusion principle. And this one tells us that there's a certain number of electrons we can fit into each orbital, or each orbital type. Basically says each orbital, each compartment can hold 2 electrons as long as they're spinning in the opposite direction. As you know, electrons have a negative charge, and things with negative charges want to repel each other. As long as you're spinning in opposite directions, they will create forces that will overcome that repulsion, but it only works for 2 electrons. So s orbitals. Again, as I said when we talked about Schrödinger-Mulliken, there's one of those per level. Because there's only one s orbital, it can hold only 2 electrons. P orbitals, there were 3 of those. There's 3 compartments labeled P, and each one can hold 2, for a total of 6 electrons. D orbitals, there are 5 per level, and each one can hold 2, for a maximum of 10. And then the f orbitals, there were 7. Each one can hold 2 for a maximum of 14. So the s orbitals on an energy level can hold 2 electrons. The p orbitals on an energy level can hold 6. The d orbitals on an energy level can hold 10. The f orbitals on an energy level can hold a total of 14. Add up all the energy levels that you have on any given level, and you can get the total for that level. Again, we said all that you have on level 1 is an s orbital. It can only hold 2. The maximum number of electrons level 1 can hold is 2. On level 2, we have s and p. You can put 2 in the s orbitals. You can put 6 in the p orbitals for a total of 8. Level 3 has s, p, and d. 2, 6, and 10 for a total of 18. And then level 4 has S, P, D, and F. 2, 6, 10, and 14 for a total of 32. Those are the maximum number of electrons that can be fit in each energy level. An idea that you're probably taught in physical science, this is where those limits come from, this quantum mechanical model. These are the primary energy levels because we know what it takes to fill them up. We don't know what 5, 6, or 7 would actually hold because we don't know enough about them. Last idea here is the Aufbau Principle, and it says the energy levels have to be filled in order from lowest energy to highest energy. And it's not exactly in the order that you would expect. You don't fill up level 1, and then fill up level 2, and then fill up level 3, and then fill up level 4. There has to be some jumping around that happens with s and d orbitals. So when you look at an electron configuration, you'll see the s and the d orbitals are out of order. This is because the s orbitals are much larger than d orbitals. So it actually takes less energy to put something into the s orbital on the next level than it does the d orbital on the current level. So when you see these electron configurations, they will be a little bit out of order. 1 is filled up, then level 2, and then you do the s and the p orbitals in level 3, jump to 4s, back down to 3d, and then back up to 4 again. Again, the s and the d orbitals end up coming out of order once you get into energy level number 3. Again, it's a size issue. They're so small that they have to be filled a little out of order. The easy way to remember the order is to write the energy levels down. And the orbitals, level 1 has just the s orbital. Then you go to your next level, keep the s's in line. It has a 2s and it has a 2p. Go to the next level. It's got a 3s, a 3p, and a 3d. And again, keep the p's in line. Then the next level, 4s, 4p, 4d, 4f. Again, we're just adding an orbital every level. When you move up to level 2, you add the p orbitals. When you move up to level 3, you add the d orbitals. Then all we're doing is adding a level, an orbital with each level that we go up. And then just draw diagonals through it. So your 1s comes down here to the 2s, which goes over to the 2p and down. These diagonal lines tell you where to go. So you start here, you move down to the next level, you go here, then you go here, follow the arrow to 3s, follow the arrow to 3p, then to 4s, then follow the arrow 3d, 4p, 5s, and follow the arrow 4d, 5p, 6s. And I will be posting a video on examples of these electron configurations using this chart and diagram so that you can see how to use them.